Hello students, welcome to my video lecture class. So this is our fifth video lecture class. So before starting today's class, I want to discuss something which I think I have missed in my second lecture. So I think I have told you up to this one, f is equal to 3 minus p, when I was told about this modified phase rule for binary system. Binary system means component c is equal to 2, and this one is for thermodynamic variable temperature, and we have taken this pressure as constant, which is 1 atmospheric pressure, and thus we get degree of freedom f is equal to 3 minus p. After that, I have to discuss this table, but somehow I have forgotten. So that's why today, first of all, I will discuss this one. So here, this is phase P, then variable V. We know that variable V is equal to P into C minus 1 plus 1. P is number of phase, C is number of component. So this is the formula to find number of variable. See this 1, you know this one is for the thermodynamic variable, which is temperature, and degree of freedom is equal to f. So if we take phase 1 or phase p is equal to 1, only one phase, then from this formula v is equal to p into c minus 1 plus 1. If p is equal to 1 and c is equal to 2, as we are taking binary system, so c always is equal to 2, we will get variable is equal to 2. So what are these two variables? One is composition variable, another is the thermodynamic variable, which is temperature. And if we put this 1 into this formula, we will get degree of freedom is equal to 2. Then if phase is equal to 2, number of phase is equal to 2, then by putting the value of p in this formula, we will get v is equal to 3. Number of variable is equal to 3. So what are these three variables? Two are composition variable and one is temperature variable. And by putting the value of p in this formula, we will get degree of freedom is equal to 1. Similarly, if number of phase is equal to 3, and by putting the value of p in this formula, we will get v is equal to v variable is equal to 4. So what are the different variables? Here it is 3 composition variables and 1 temperature variable. And when we put the value of this p in this formula, we will get f is equal to 0. So for binary system, this is all for binary system. So for binary system, by putting different values of p, we can get the values of degree of freedom, which are for one phase degree of freedom will be 2, for two phase degree of freedom will be 1, and for three phase degree of freedom will be 0. So in my last lecture, I have discussed about two phase region where v is equal to 3, number of variable is equal to 3, And what are these variables? One is CL, one is CS, and another is temperature. CL, CS, and temperature, these are the three variables. Two composition variable, one temperature variable, and degree of freedom is equal to 1 for two phase region. So I already told you, if we take two phase, variable will be 3 and degree of freedom will be 3. And here also we can see, if we take two phase region, variable will be 3 and these are the variables, and degree of freedom will be 1. So now this is our today's topic, microstructural changes on cooling a copper 50% nickel alloy. So in the last class I told you about this tie line where the temperature is constant. Temperature is constant and we have taken the composition Cl and Cs at constant temperature. Now we will vary the temperature and fix the composition. Fixed composition means 50% of copper and 50% of nickel. So 50% of copper and 50% of nickel, let us say this point. And here from this point to this point, temperature is increasing. Temperature is increasing. And here it is 50% of copper and 50% of nickel. Let us say this composition is C naught. In this side it is temperature, in this side it is composition axis, and here the temperature is T1. So now we will see the microstructure in this place, T1 temperature. Okay, so at T1 temperature point, the composition is C naught, which is 50% of copper and 50% of nickel. So what will be the microstructure at this point? So we have all liquid in this place. So we can see this kind of microstructure as at this point we have only liquid phase. This is above of this liquidous line. So as it is above of this liquidous line, so we have only liquid phase in this point, and due to this liquid phase we will get this type of microstructure where we have all liquid phase. Now we will take temperature between liquidus and solidus line. This is our liquidus line and this is our solidus line, and we will take one temperature in between this solidus line and liquidus line. So first of all, as in this case we have constant temperature, constant composition which is consist of 50% of copper and 50% of nickel, which is C naught. So now we are taking a temperature which is in between this liquidus line and solidus line. This point is T star. Here, let us say we have one point, and in this position we have another point. This point is T1 and this point is T2. Now, in this place, where above of this liquidus line, we have liquid phase, and below this solidus line, we have alpha phase. And in between this liquidus line and solidus line, we have liquid plus alpha. So here we have one composition, and in this place also we have one composition. We are naming this composition as Cl and this composition as Cs. Let us say at this point the composition Cl, which is composition Cl, we have 10% of nickel and 90% of copper. And at this point we have 15% of copper and 85% of nickel. So this one is one tie line where temperature is constant, and we are taking this point. And we will see the microstructure at this point, where the point is in between liquidus line and solidus line. So as we have both the solid phase as well as liquid phase in this case, so the microstructure will be consist of alpha phase as well as liquid phase. So these are our alpha phases, alpha components, and remaining is liquid. So here you can see in the microstructure at this point we are getting this type of microstructure, which is consist of liquid phase as well as alpha phase. liquid phase, alpha phase means solid phase. Now we will go in this place where we have all solid phase, means below this solidus line. So first of all we have to draw this composition, constant composition line, which is C naught. C naught is consist of 50% of copper and 50% of nickel, and taking one particular point at this place below this solidus line, this place, and let us take this temperature is equal to T star. So now we will see at this temperature which is below, which is present below this solidus line. So the microstructure will be, in this case the microstructure will be consist of all solid or alpha like this. All these are alpha phase. So below this solidus line, if we take one temperature point where the composition is C naught, which is consist of 50% of copper and 50% of nickel, the microstructure will be like this, where we have all alpha phases. Okay, so here we have three different microstructure at three different temperature point, but the composition is constant, which is C naught, and it is consist of C naught is consist of 50% of copper and 50% of nickel, and these are the three microstructure. If we take this point where the temperature is above of this liquidus line, so the microstructure will be consist of all liquid phase, and this will be like this. And if we take in between this liquidus and solidus line, so the microstructure will be like this, which is consist of liquid phase as well as solid phase. And if we take a temperature point which is below this solidus line, so the microstructure will be like this, where we have only solid phases. Now we will see the microstructure at different point of a tie line, and I am fixing the temperature at 1300 degree centigrade. So at 1300 degree centigrade, if we draw a tie line, so what will be the microstructure at different composition that we will see right now. So here we have one diagram. So let us say this point is 1300 degree C. So this is our tie line. tie line, and the temperature is 1300 degree centigrade. So now we will see the microstructure for different composition. Let us say this composition, this at this point the composition is Cl, and at this point the composition is C alpha or Cs. Let us say Cs. And the temperature is constant. At the previous one where we have seen three different microstructures, so that was for constant composition, which was C naught. This C naught was consist of 50% of copper and 50% of nickel, and we have seen for that constant composition at different temperature we will get different microstructures, or by varying the temperature we can change the phase of one composition. Now we have constant temperature and we are varying the composition. So at constant temperature, by varying the composition, we can get different different types of that microstructure. So first of all, we will see at this liquidus point the composition Cl. So what will be the microstructure at this point? So we know at this point we have only liquid phase. So for this liquid phase, the microstructure will be like this, where we have all liquid phase. So this one is for Cl. This one is for Cl. Now we will take a point which is near about this Cl composition. Let us say this point. This is near about this Cl point, and we are naming this one as C1. And we will see right now, we will see the composition at C1 point. What is the microstructure at this C1 composition? This is near about this Cl line, and here the liquid state is converting into solid phase. So as it is near about this liquidus line, liquid phase will be greater than the solid phase. So in this point we will get small part of alpha phase. These are all alpha phase, because solidification just started. That's why a little number of solid phase or alpha phase and greater amount of liquid phase. So the microstructure, this is the microstructure at point C1. C1 point, the microstructure will be like this, where the solidification just started. Now we will take another point which is near about this CS composition, let us say this point, and we are naming this point as C2. Now we will see the composition, sorry, the microstructure of this composition which is near about this solidus line. So as this is near about solidus line, so solid part will be maximum in this point, and little amount of that liquid phase. So most of the part of this point has become into solid. So all these are alpha phase, and little amount of liquid phase. Like this. So this microstructure is for this C2 composition. For this C2 composition, the microstructure will be like this. For this C2 composition, which point is or which composition is near about this solidus line, the microstructure will be like this. Maximum part is consist of alpha phase and little amount of liquid phase. Now we will see the microstructure at CS. This point, this is CS. So now we will see the microstructure of this CS composition. So as it is lying in this solidus line, so it is a general knowledge that at this point we will have only alpha phase, no any liquid phase. So the microstructure will be like this. All we have only solid phase, no any liquid phase, as the point is lying in the solidus line. So this is for CS. So here we can see the different microstructure at constant temperature. So we can, from this diagram and this diagram, this one where the temperature is varying about this line and composition is constant, and here the composition is varying but the temperature is constant. So in both cases the liquid phase is converting into solid phase. So to change the state of a matter from liquid to solid, either we can go for constant temperature, which is this one, and vary the composition, or we can change the temperature and fix for fixed composition. For fixed composition, we can change the state of a matter by varying the temperature, and for that varying composition, we can change the phase at constant temperature. So here, right now, I have discussed two cases where we are changing the state of matter by in one case by varying the composition, and in another case by varying the temperature. So that's all for today's lecture. Now I will discuss about some queries which I get from the comment section of my previous lectures. The first question and second question has been asked by a same person. So that's why I will discuss these two questions together. The first question is the tie line drawn only in two-phase region of the diagram or through the entire binary diagram? And the second question is, can we draw tie line only in isomorphous system or also in complex binary diagram? Yes, we can draw it not only in isomorphous system as well as in complex diagram, complex binary diagram. Also, we can draw this tie line in tertiary diagram also, where we have three components. So actually, I think I have to tell about the difference between phase of a matter and state of a matter in this regard. Then your knowledge of in this regard will be clarified. So now I will talk about difference between state of matter and phase of matter. First is state. So this state, we can classify state as solid state, liquid state, and gaseous state. And in case of phase, we can classify phase by considering three different factors, which are structure, state, and composition. So from here, we can say that state is a subset of phase. State is a subset of phase. Also, we can say principal phases are states. Principal phases are states. Let us understand it with the help of an example. We are taking the example of ferrite. Ferrite, which is a alpha iron. So we are converting this ferrite into gamma iron, which is basically austenite. So if we consider the state of this ferrite and austenite, ferrite is alpha iron and austenite is gamma iron. The state of both austenite and ferrite are same, as both are solid, but the structure of these two are not same. This ferrite has BCC structure and austenite has FCC structure. So state of these two phases are same, solid phase, but the structures are different. So due to this different structure, we will see ferrite is one phase and austenite is another phase. Let's say this is phase 1 and this is phase 2 due to difference in their structure. Now, if we talk about this state change, state change means solid to liquid or liquid to solid. Solid to gas or gas to solid. And liquid to gaseous or gaseous to liquid. But if we talk about phase change, phase change means structure change state change and composition change. So the above mentioned example was for structure change. Now we will talk about composition change. Ferrite, we are taking the example of ferrite again. By adding carbon in ferrite, it will convert it into cementite. The cementite is consist of 6.67% of carbon. So here we are changing the composition by adding carbon with ferrite. We are changing the composition of ferrite into cementite. So the structure of this ferrite is BCC. We know that BCC, and the structure of cementite is orthorhombic. So that's why here the composition of these two are different. Also the structure of these two are different. That's why the phase of these two also will be different. Let us say this is phase 1 and this is phase 2. But in this case, both the state of both ferrite and cementite are same. Both are solid state. Both are in solid state, but the phase is different due to change in or due to their difference in composition and structure. So, phase of matter explains uniform chemical and physical properties of matter, whereas state explains the form of the matter at a given temperature and pressure. So, the state of a matter may consist of different chemical and physical properties, but phase of a matter always will be uniform. So this is the difference between phase and state. Now I think you can easily understand, as you now you know about the difference between phase and state. uh, as we have only 3 states, but number of phases may be above 3, like alpha phase, beta phase, gamma phase, like this, liquid phase. So right now I already told you about 4 different phases: liquid phase, alpha phase, beta phase, gamma phase, like this. But state always 3: solid state, liquid state, and gaseous state. So your first question, that was, is the tie line drawn only in the 2-phase region? No, we can draw it in 3-phase region also. Okay, or through the entire binary diagram. Yes, we can draw it and for the entire binary diagram. And the second question is, can we draw tie line only in isomorphous system? No, we can draw it for complex binary diagram also, as well as for that tertiary diagram also, where we have number of component is equal to 3. Now come to the last question, which is, if we take atomic percentage instead of weight percent, then what will be the phase diagram? So in this regard, I want to say, basically this is a question of chemistry, but still I will discuss it. So I will discuss it with an example. I am taking the example of water. Water is consist of hydrogen and oxygen. Here, 2 atom of hydrogen is reacting with 1 atom of oxygen and producing 2 atom of water. So from here we can say 66.5% of hydrogen is reacting with 32% of oxygen and producing water. So if we change this percentage, this atom percentage, so the product will change. How? Let us say we are taking right now 50% of hydrogen and 50% of oxygen. Okay. So it will become H2O2, means hydrogen peroxide. So if we change the percentage of atom, the product will change. In this case it was water, but in this case it becomes hydrogen peroxide. So I think from here you can understand, or you can get your answer. So that's all for today. Tomorrow I will discuss about lever rule or lever arm rule. Okay, thank you.